All right, we're going to look now at expanding binomial expressions. So first of all, I just want to remind you, a binomial is an expression with two terms. Binomial, by two terms. We are going to expand binomial expressions. So what that means is we're going to have any two-term expression to some exponent. And you've looked at things like x plus 5 all to the power of 2. And we've squared those and you've done FOIL. But when you continue to expand something then to the third, to the fourth, to the fifth, whatever exponent higher than 2, it gets much more complicated because then you have to FOIL a lot of times and it becomes very, very complicated and it turns into a very long problem. You need a whole sheet of paper. So instead, binomials to a power can be expanded using Pascal's triangle. Well, what is Pascal's triangle? If you have never heard of Pascal's triangle before, Pascal is a very famous mathematician and has this very famous triangle that he created that is used for a lot of different things in math, and one of them is expanding binomials. Pascal's triangle is made up only of numbers, and there's a pattern to how to get to the next row using the previous row. It starts out with a 1 up at the top. That's the first row. The second row is 1 and then 1. Any as you continue down every row, the beginning and ending number will always be a 1. And then the next, any other numbers, you go to the previous row and add up the numbers directly above that. What I mean by that is I'm going to take 1 and 1 at the end. Now we're going to take 1 and 1 makes 2. So the second row is 1, 2, 1. Oh, sorry, third row. The third row is 1, 2, 1. Now I'm going to expand it again. 1's on both of the ends. Now I'm going to add 1 and 2 gives me 3, and 2 and 1 gives me 3. And as I'm expanding, you should notice a couple of things. So first is it starts with 1 term, and then there's 2 terms, and then 3 terms, and then 4 terms. So how many do you think there's going to be in the next one? 5 terms. Also, like I said, it always begins and ends with 1. And the second number in each row should increase by 1 from the previous row. So the second number here is a 0. The second number here is a 1, increased by 1. The second number here is 2, which increased by 1. The second number here is a 3, increased by 1. Another thing you will notice is if I draw a line of symmetry straight down the middle, it should be symmetrical. So this one's just 1. Here I've got 1 and 1 on both sides. Here I've got a 2 in the middle, 1 and 1 on both sides. If I split this row down the middle, I've got a 1, 3, and then a 3, 1. To get to the next row, I would expand with 1s on both ends. 1 and 3 makes 4. 3 and 3 makes 6. 3 and 1 makes 4. So 1, 4, 6, 4, 1. So you could continue that as you go, always expanding with 1s on the outside. 1 and 4 would make 5. 4 and 6 would make 10. 6 and 4 would make 10. 4 and 1 makes 5, and end with a 1. There is not an easy way to be able to find, like, well, what's the 100th row in Pascal's triangle without knowing the 99th and the 98th and the 97th and so on and so forth. So for the most part, I'm going to stick with probably the first 10 or fewer rows you needing to know. But the other thing is, once you have it one time on your paper, you have it and it's there. You don't need to like rewrite it every time. You just need to know then what row are you working with. So let's talk about how to use this to expand binomials. You can expand a binomial, does not work with trinomials or anything else, to any power, any exponent, using Pascal's triangle. The number of your exponent on your binomial, so if you were doing like something and it's to the power of 5, that exponent, is the second number in the row you will use from Pascal's triangle. So if my exponent was a 5, I would be using this row down here because the second number here is a 5. If my exponent was to the power of 3, I would be using this one because the second number is to the power of 3. The row is all of the values you will use for each term in your expansion. So when I'm going to expand, if I had something to the power of 3, my final answer should have 1, 2, 3, 4 terms. And the first term is going to be multiplied by a 1, the second by a 3, the third by a 3, the fourth by a 1. Then each term from left to right will start with your first term from your binomial to the power of the exponent on that binomial. And then each term moving to the right will have 1 less power until the last term has nothing from the first term. So if I'm using something to the power of 3, it's going to be the first term cubed, the first term squared, and then the first term and nothing. And the second term of your binomial will go kind of in reverse. The first term will not have that term, and then moving to the right, there will be 1 more until the last term has the same power as your binomial. So from the second term, it would have none of those, 1 of those, squared, and cubed. So let's look at what that means and look at some examples. So when you have anything here, it's not always going to be x plus y. It's going to be 5x minus 7 or whatever it might be to n, where n is your exponent. So n could be 2, it could be 3, it could be 17, whatever it's going to be. N identifies your row from Pascal's triangle. Whatever n is, you look at the second number in the row. That tells you you're going to use that whole row. It's going to be, the first one's always going to have a 1 on it, right? Pascal's triangle starts and ends with 1. And you'll take your first term to the nth power, whatever n is. If it's 5, you use 5. Now, these here, these n's and a's, as you keep going, are going to come from Pascal's triangle. The second term is going to now have x to 1 less than the exponent and 1 of the y's. The next term is going to have 2 less of the x's, the first term, and 2 of the y's. So on and so forth until you're down at the end. It's going to have, get rid of this, it should not have an x, shouldn't have that. Should have the y's to whatever power. And then here it's going to have 1 less of the y's and 1 x, 2 less of the y's, but 2 x's, working your way. It becomes easy as we go through examples. So let's just look at an example and see how this works. So first thing you need to make sure you do is identify your exponent is a 3. So you need to go back to Pascal's triangle to identify your coefficients we're going to need. If it's a 3, here's our row because the second number is a 3. So I'm going to need 1, 3, 3, 1. And you want to leave lots of room in between because you have more things to use. Now you're going to take the first term. Your first term here is just x, so this is easy. We're going to start with x to your exponent, and then work your way down until you have none. Then you're going to take your second term, which for us is y, and I do want to pay attention, it's a positive y. We'll get to an example when there's a negative what to do. You're going to start with nothing on the first one, and then work your way up. So none, 1, squared, and the last one should match the exponent from your original exponent. Now, since our operator was a plus, all of these are plus. Nice and easy. And you would check to see, is there anything to simplify? In this case, no, but we'll get to some here very shortly where we do have some things to simplify. I don't need that 1 in front of my x cubed though, so you could just write it as x cubed plus 3x squared y plus 3xy squared. And similarly, you don't need the 1 in front of your y cubed. There it is expanded. This time we're to the 4th power. If we're to the 4th power, now we want this round because our second number is a 4. So 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Our first term is n. So n to the 4th, work your way down until the last one shouldn't have any n's. Our second term is a -3. That negative is important. So our first term doesn't have any of those. Our next term, we're going to have 1 of those, 2 of those, 3 of those, and 4 of those. And we're going to start with plus signs in between. I did say we're going to start. It's not going to stay that way. We had a minus sign in between our n and our 3. They're not all going to switch to minus signs, but we have some simplifying to do. 1 n to the 4th is just n to the 4th. But this term, I can do some simplifying. 4n to the 3rd times -3. 4 times -3 is -12 n to the 3rd. So I just multiplied 4 times -3 to get -12. So there's a minus sign there now. In the next term, -3 squared is 9. Right? Negative times a negative is a positive. 3 times 3 is 9. So I have 6 times 9, which is 54 n squared. And that's positive now. So plus 54 n squared. In the next one, I have another exponent I need to simplify. -3 to the 3rd. So that's a negative times a negative times a negative is a negative. And 3 times 3 is 9 times 3 is 27. But then I have that 4 also. That is 4 times -27. Feel free, use your calculators as you're doing these problems. You're going to want it. But 4 times -27 is -108 n. You also could just straight in your calculator type in 4 times, and then in parentheses, -3 to the 3rd, and it'll straight give you -108 instead of doing it in 2 steps. And in the last one, I just have 1 times and then -3 to the 4th. Well, since it's 4th, that means I have 4 negatives. 4 negatives make a positive. 3 to the 4th. Well, 3 to the 3rd is 27. 27 times another 3 is 81. There is your expanded answer. And you maybe notice here, positive term, negative term, positive term, negative term, positive term. When you have a minus in between your 2 terms, it should go every other one. So if you have a positive for your first term, up here this n is positive, and a negative for the second term, it should start positive, negative, so on and so forth until you're done. This one is to the 5th power. Go back to Pascal's triangle. I need that bottom one, 1, 5, 10, 10, 5, 1. And you could put plus signs in between there. In this case, since it is a plus in between, you know they're going to be pluses anyway. If it was a minus in between, you could do your every other one. Or you could start with pluses and then turn them into minuses like we did in the last example. All right, this time, my first term is 3x. So I need 3x all to the 5th. And then the next one, I need 3x all to the 4th. And then 3x all to the 3rd. 3x all squared, and then 3x. And nothing on the last one with the 3x. And then my second term is a 1. But come on, let's think this through. 1 to any power is 1. And 1 times anything is just that anything. So really I could skip that step. If you wanted to have it feel free, you'd start with nothing, and then 1, and then 1 squared, 1/3, 1 to the 4th, 1 to the 5th on all those terms. But that's just extra steps in your life that you don't need. So instead, let's just start simplifying. Remember when you have those parentheses, the 3x all to the 5th means I have 3 to the 5th and x to the 5th. 3 to the 5th, this is where you're going to want your calculators. 3 to the 5th is 243, x to the 5th, plus 3 to the 4th is 108, but then I need to times it by 5. It's 405, x to the 4th. 3 to the 3rd is 27, times 10 is 270, x to the 3rd. 3 squared is 9, 9 times 10 is 90, x squared. This one doesn't have an exponent, it's just 5 times 3 is 15x, plus 1. And we've got one more example. M to the 3rd minus 7n, all to the 4th. Pascal's triangle says I need 1, 4, 6, 4, 1. And since I have a minus sign in between here, I know that I'm going to have a positive, a negative, a positive, a negative, a positive. Because my first term, m cubed, was positive, and my second term, minus 7n, is negative, that's how they're going to go. Now I'm going to take my first term, is m to the 3rd. That needs to go to the 4th. And then m to the 3rd to the 3rd. M to the 3rd squared, and m to the 3rd, and then nothing on the last one. Now I already dealt with my negative when I did one positive, one negative every other time. So now I can just focus on the 7n. If you didn't deal with those like I did, you would need to do negative 7n all to your exponents, and that would then take care of your positives and negatives. No 7n's on the first one. 1 on the next one, 2 on the 3rd, then 3, and then 4. Your m to the 3rd to some exponent is a power to a power. You multiply those exponents. 3 times 4 gives you m to the 12th minus m to the 3rd, 3 times 3 is 9. So I'm going to have m to the 9th. And then I have a 4 times a 7 is 28. M to the 9th, n. So 4 and 7 give me my 28. M to the 3rd is the m to the 9th. And then just bring down your n. Plus m to the 3rd to the 2nd will be m to the 6th 7n squared is going to be 49n squared. And you have 49 times a 6 is 294 n to the 6th n squared. Remember, we had n squared up there. Minus. Now this one just has an m to the 3rd. No exponent on that, so we're going to have an m to the 3rd. 7 to the 3rd will be 343 n to the 3rd, but that 343 needs to be times by 4. So that's going to give me 1,372 n to the 3rd, n to the 3rd, plus 7 to the 4th is 2,401 n to the 4th. There is your final expanded answer.